Hello everyone, and welcome back to the Calculus 1 video lectures. Today we are going to be covering one major application of the chain rule, which is a process called implicit differentiation. So we have two different ways of defining functions. So one is explicitly defined. An explicitly defined function is where y is by itself, y is a function of x. So y is written as equals something x. So y equals x to the fourth plus 1 is explicitly defined. Y is the function of x, and y is by itself. Now this is not implicit. This is called implicitly defined. Y to the fourth plus xy equals x cubed minus x plus 2. Y is not by itself, and we are not going to get y by itself. And you've actually seen expressions that are implicitly defined before when you learned equations of circles. The equation of a circle is implicitly defined. And one major circle that you have covered in previous courses, specifically in pre-calc, was the unit circle. The unit circle, which has equation x squared plus y equals 1, is an implicitly defined equation. And if you remember the graph of the unit circle, it looks something like this. It's a circle with a radius of 1 and a center of the origin. Now, this is an example of an equation that is defined implicitly. And notice it doesn't pass the vertical line test. Circles don't. But this graph still has tangent lines. There is still a tangent line, let's say at this point right here. So these do still have tangent lines, but we cannot get y by itself. Because if you were to actually take the unit circle equation and get y by itself, you would get y is equal to the square root of 1 minus x squared, which is a semicircle. So if you actually do get y by itself, you are only going to be looking at a limited part of this from here to here, the semicircle from here to here. You will be eliminating whole entire half of this circle by getting y by itself. So with implicitly defined functions, we are not going to get y by itself because we are actually taking away features of the graph. And because there are still tangent lines that exist on the unit circle for other points that are outside of this semicircle, we are not going to be getting y by itself. Instead, we're going to be using a separate process called implicit differentiation to take derivatives of equations like the unit circle written as is. Now, since the unit circle is still graphed in the xy plane, y is still the vertical axis and x is still the horizontal axis. So on this plane, y is still a function of x, and that is going to be extremely important. So we're going to be taking derivatives of equations that are defined implicitly, where you have one independent variable and one dependent variable, and the dependent variable is dependent on the independent variable. Now, x and y are not always used, but these are very common. X is the independent variable and y is the dependent variable. So in other words, x is the only actual variable here and y is a function of x. Now, in implicitly defined equations, y is not by itself, nor are we going to get y by itself, because if you get y by itself, you are taking away parts of the graph, and you are eliminating parts of the graph which could still have tangent lines. So we're going to be taking derivatives of implicitly defined functions written as is, and not even trying to get y by itself. So implicitly defined equations still have tangent lines, which means they still have derivatives. And the core at the process of taking a derivative of an implicitly defined equation is the chain rule. So the chain rule is at the heart of the process called implicit differentiation. I think the easiest way to demonstrate how to do this is to just do an example. We're going to actually do the unit circle because this is a really easy equation to start with. So remember, y is still a function of x, and it is actually important what we are computing, and we're actually going to be using Leibniz's notation pretty much exclusively here, because Leibniz's notation, while more complicated looking, does kind of spell out for you what is the independent variable and what is the dependent variable. The independent variable is always this variable here on the bottom. So because the x is on the bottom, that means x is the independent variable. whatever letter is here is the dependent variable or the function. So since this is dy dx, because y is on the top and x is on the bottom, this means that y is a function of x. So what we're going to be doing is we are going to be taking the derivative using, normal power rules, but anytime that we see a y, we have to remember that it is not actually the variable. X is the variable here. Y is a function of x. So anytime that we run into the derivative involving y, we have to remember that y is a function. And if that function is being raised to any powers, or if anything else is being done to that function, we are actually going to need the chain rule. And yes, we are going to be doing some simplifying here because it is specifically asking us to compute dy dx. You're going to find that when we actually take this derivative, dy dx is going to be in that equation somewhere, but dy dx needs to be by itself. So the main simplifying part here is going to be getting dy dx by itself. But let's first take the equation of the unit circle as is, and we are going to be taking the derivative with respect to x of every single term on both sides, because a derivative is like any other operation. Whatever you do to one side of an equation, you need to do the exact same thing to the other. So I'm just going to go term by term, and I'm going to take the derivative with respect to x of every single term on both sides of this equation. Now, if the variable in the expression matches the variable that you're differentiating with respect to, you do not need any chain rule and you do not need anything special. So we're going to take the derivative of x squared with respect to x. So the variable in our expression matches the variable we're differentiating with respect to, so we don't need anything special, just power rule, derivative is 2x. However, for the next term, we are taking the derivative of y squared with respect to x. So the letter in the variable in the expression y is not the same as the variable we're differentiating with respect to, so this requires chain rule. Remember, y is a function of x. So in this case, the squared is going to be the outside function, and y itself is actually going to be the inside function. And you might remember from the last video, with chain rule, you always start with the derivative of the outside. So the derivative of the outside is going to be 2, and you're going to leave y alone and then decrease the power by 1. Then, after you take the derivative of the outside, you're going to take the derivative of the inside. Y is a function of x. So the derivative of y with respect to x, I'm going to notate that as dy dx. Derivative of y with respect to x, and that's going to be the derivative of the inside. Then don't forget there's an equal sign here. Derivative of 1 is 0. Derivative of a constant is always 0. So at this point, the calculus step is done. However, it's specifically asking for dy dx, so we need to do a little bit of work to get dy dx by itself. So to get dy dx by itself, I'm going to start by moving this 2x over to the other side. So I'm going to subtract 2x from both sides. That will give me 2y times dy dx equals negative 2x. Then we're going to finish getting dy dx by itself by dividing both sides by 2y. So that will give us dy dx is negative x over y. Now notice that the original function was implicitly defined, so the derivative is also implicitly defined. So the original had x's and y's mixed together, so the derivative also has x and y's mixed together. Now, the reason why we're using Leibniz's notation is because Leibniz's notation tells us what the variable we're differentiating with respect to. So it tells you when you need to use chain rule. If the variables match, you do not need chain rule. If the variables do not match, you need chain rule. So there's a little difference between these two, but there's a big difference. So starting with d dy of sine y. We are taking the derivative of sine y with respect to y. So because the sine y is in terms of the same variable that you're differentiating with respect to, you don't need chain rule. So derivative with respect to y of sine y is just cosine y, and that's the end of it. Now, if you were taking the derivative with respect to x of the sine of y, the variable in the expression does not match the variable you're differentiating with respect to. So sine of y is not in terms of the same variable that you're differentiating with respect to. That means that y is a function of x and it requires chain rule. So the derivative of the outside would be cosine of the inside left alone. Then you would multiply it by the derivative of the inside, which is dy dx. So pay attention to what variable you're differentiating with respect to and whether the expression is in terms of that same variable. You're also going to use Leibniz's notation pretty much exclusively because it will tell you when you need to use chain rule and when you don't. Now, the whole purpose of finding these derivatives is so that you can calculate the slope of the tangent line of these curves at any particular point. So the derivative of the unit circle dy dx we just found was equal to negative x over y. So we're going to use that to calculate the slope of the tangent line of the unit circle at the point 1/2 comma root 3 over 2. So again, on the unit circle, this point is about right here. And it has a tangent line, and we're going to be calculating the slope of that tangent line using the derivative. Now, the derivative involves both x and y, which means that you need both the x and the y coordinates of the point of tangency in order to find the slope of the tangent line. So if we take our derivative dy dx, and if we evaluate it at 1/2 comma root 3 over 2, what that will give us is the slope of the tangent line of the unit circle at this point. So I'm going to plug negative 1/2 in for the x coordinate. I'm going to plug root 3 over 2 in for y. And then after a little bit of simplifying, you get negative 1 over the square root of 3, which simplifies to negative root 3 over 3. So that is going to be the slope of that tangent line of the unit circle at this point of tangency. So we're going to try that again. We're going to take a different function this time, and we're going to be calculating dy dx. Pay attention to what it's asking you to calculate, dy dx. The variable on the bottom is the variable you're differentiating with respect to. So since x is on the bottom, our independent variable is x, and we're going to differentiate with respect to x. And since y is on top, that means y is a function of x. So we're going to start with taking the derivative with respect to x of every single term on both sides of this equation. So we have the derivative with respect to x of the sine of xy equals derivative with respect to x of x squared plus derivative with respect to x of y. And we're going to go to kind of piece by piece, and we're going to take their derivatives. So with the left side of the equation, this is clearly a function composition, where sine is the outside function, and x times y is the inside function. So x times y is a product, so you will need product rule, but you only need product rule when you take the derivative of the inside function. So here we go. We're going to use chain rule. We're going to start off with the outside function. Derivative of sine is cosine of the inside left alone. Then we're going to multiply it by the derivative of the inside. And since derivative of the inside is going to use product rule involves more than one term, you do need to use parentheses. So the first part of the product is x, second part of the product is y. So derivative of the first part of the product is 1 times the second part of the product left alone, plus the first part of the product left alone, times derivative of the second part of the product. Now the second part of the product is y, and remember we're differentiating with respect to x. So the derivative of y with respect to x is just dy dx. Now before we get to the other side of the equation, I do want to point out that unless y is being raised to like some other power, you don't need chain rule. So then for the other side of the equation, we're taking the derivative of x squared with respect to x. So x squared is in terms of the same variable we're differentiating with respect to, so we don't need anything special. Its derivative is 2x. Plus derivative of y with respect to x. These variables do not match. This is not in terms of the variable we're differentiating with respect to. Now, y is not being raised to any powers. Y is not inside of a sign. It's just y by itself. So you don't actually need chain rule here, but you are going to represent its derivative as dy dx. So the calculus step is done. Now we get to do a whole bunch of algebra to get dy dx by itself. So as complicated as this looks, you're actually going to find that getting dy dx by itself is going to be a very similar process to getting a variable by itself in a linear equation that you learned way back in like Algebra 1. So we're getting dy dx by itself. There's one of them over here and one of them over here. So we've got dy dx's on both sides of the equation. And one of your dy dx's is inside parentheses. You did need these here. So how do you clear out parentheses? Well, you clear parentheses by distributing. You distribute whatever the parentheses are being multiplied by. So these parentheses are being multiplied by this cosine of xy. So I'm going to clear out these parentheses by distributing cosine of xy. So cosine of xy times y is y cosine of xy. Then cosine of xy times x dy dx is plus x cosine of xy times dy dx. Don't forget there's another side to this equation, so equals 2x plus dy dx. So now at least the parentheses are gone, but you still have what you're trying to get by itself on both sides of the equation. So it would probably really help if all of the dy dx's were at least on the same side of the equation. So what we're going to do at this point is we're going to move all of the dy dx's onto one side of the equation, and everything that does not involve a dy dx is going to be moved onto the other side. So dy dx here is easiest to move, so I'm going to move this over to the other side by subtracting it. And while we're at it, this y cosine of xy here, this does not involve a dy dx, so let's get rid of it. So we're going to move this term, which does not have a dy dx, over to the other side. So after you move a whole bunch of terms around, this is what we end up with. We end up with x times the cosine of xy times dy dx minus dy dx equals 2x minus y cosine of xy. So at least all of the dy dx's were on one side of the equation, and anything that did not have a dy dx moved on to the other side. So then, now on the left here, there are only two terms technically, and both of these terms have a dy dx in them. What do you do when both terms have a common factor? You can factor out that common factor. So what I'm going to do from here is I'm going to factor out a dy dx out of each term on the left side here. So I'm going to write dy dx out front, put the leftovers in parentheses. So we have 2x minus y cosine of xy. So when I remove a dy dx from this first term, I'm left with x cosine of xy. Then when I remove the dy dx from the second term, I'm left with minus 1. Then, to finish getting dy dx by itself, you are going to divide both sides by whatever dy dx was being multiplied by. So to undo that multiplication, I'm going to divide both sides by x cosine of xy minus 1. So divide this by x cosine of xy minus 1. So we get a final derivative, dy dx, of 2x minus y times the cosine of xy all over x cosine of xy minus 1. And as long as dy dx by itself, that is pretty much good. So this is going to be our final answer. So then for this next one, we are going to be finding the equation of the tangent line at the point 1, 1 of this curve. This is an implicit curve. Now, in order to write the equation of a tangent line, what are the two things that you need to write the equation of a line? Well, you need a point and you need a slope. So to write the equation of the tangent line, you need the point of tangency and you need the slope of the tangent line. We have the point of tangency. What we are missing is the slope of the tangent line. So we need to find the slope of the tangent line first. Slope of a tangent line involves the derivative. So we're going to start by finding the derivative, and then we're going to plug in our point. So to find our derivative, that is going to require implicit differentiation. So I'm going to start by taking the derivative with respect to x of every single term on both sides. Now I'm going to run out of room very fast for this one. So we're just going to take the derivative with respect to x of each term one at a time. Remember, if your expression is in terms of the same variable you're differentiating with respect to, you do not need chain rule. If it is not in terms of the same variable, you need chain rule. So taking the derivative of y to the fourth with respect to x, these variables do not match, so we need the chain rule. The power of 4 is the outside function. Y itself is the inside function. So the derivative of the outside is going to be 4y cubed. Then we're going to multiply it by the derivative of the inside, derivative of y with respect to x, dy dx. Plus, we're going to move on to the next term. So we're taking the derivative of x times y with respect to x. So x times y, this is a product. Its derivative requires product rule. So derivative of the first part of the product, derivative of x with respect to x is 1 times second part of the product left alone. Then we're going to add to it the first part of the product left alone times the derivative of the second part of the product. So the derivative of y with respect to x is dy dx equals, then we're going to take the derivative with respect to x of the entire right side, which luckily x cubed minus x plus 2, no special chain rule required here. So derivative of x cubed is 3x squared. Derivative of minus x is minus 1. Derivative of 2 is 0. So then what we get to do is we get to get dy dx by itself. Now luckily there's no parentheses to clear out and all of the dy dx's are at least on the same side. However, this y here does not have a dy dx in it, so I am going to move it onto the other side. So that will give me 4y cubed dy dx plus x dy dx equals 3x squared minus y minus 1. So now that all of the dy dx's are on the same side and the only thing on the left-hand side has a dy dx in it, we have a greatest common factor of dy dx, so I'm going to factor a dy dx out of each term on the left side. So what's left over out of this first term is going to be a 4y cubed, plus what's left over out of the second term is x. And don't forget that equals 3x squared minus y minus 1. Then we're going to finish getting dy dx by itself by dividing both sides by 4y cubed plus x. So we get a derivative dy dx of 3x squared minus y minus 1 all over 4y cubed plus x. Now the whole reason that we are getting dy dx by itself is to find the slope of the tangent line. That's the whole point of derivatives. So the whole point of getting dy dx by itself is so that you can then evaluate it at a given point, plug its x coordinates in for x, plug its y coordinates in for y, and you will instantly get dy dx. So to calculate the slope of the tangent line, what we're going to do is we're going to take our dy dx and we're going to evaluate it at the point 1, 1. So I'm going to plug the x coordinate into every single spot I see an x, and I'm going to plug the y coordinate into every single spot I see a y. So that will give us 3 times 1 squared minus 1 minus 1, all over 4 times 1 cubed plus 1. And that gives us a slope of a tangent line of 1/5. So now that we have the slope of the tangent line and the coordinates of the point of tangency, we can then wrap it up to get the equation of the tangent line. So the equation of the tangent line is y minus the y coordinate of the point of tangency, 1, equals slope of the tangent line, 1/5, times x minus the x coordinate of the point of tangency, 1. Let me try writing that again without a glitch. Maybe. There we go. So then that is going to be the equation of your tangent line. And remember, if you need to write it in slope-intercept form, all you have to do is distribute the 1/5 and then add 1 to get y by itself. So then for this next one, we're going to be calculating dy dx of 2 times x plus y to the 1/3 equals y. So since we are calculating dy dx, that means y is a function of x, and we are differentiating with respect to x. So what I'm going to do is I'm going to take this equation, and I'm going to take the derivative with respect to x of both sides. Now the left here requires all sorts of chain rule. So the outside, remember the constant multiple of 2, nothing's going to happen with that. So that constant multiple of 2 is just going to stay there. The outside function is this exponent of 1/3. The inside function is x plus y. And remember, we're taking the derivative with respect to x. So we're going to start off with the derivative of the outside. It is a numeric power, so we're going to move down the power, leave the inside alone, and decrease the power by 1. 1/3 minus 1 is negative 2/3. Then we're going to multiply it by the derivative of the inside. Now, if the derivative of the inside involves more than one term, you have to use parentheses. So derivative of x with respect to x is 1, plus derivative of y with respect to x is dy dx. And since this is getting multiplied by the entire derivative of the inside, you do need parentheses here. Then on the other side, derivative of y with respect to x, since y is not being raised to any powers, and we're not taking a sign of y or anything like that, it's just y, we're going to just represent that derivative as dy dx, and we do not need chain rule. So then we're going to now get dy dx by itself. They're on both sides of the equal sign, and one of your dy dx's is inside of a parenthesis. To clear out parentheses, you're going to distribute. You distribute by whatever the parentheses are being multiplied by. So remember, this is all one giant term. So we're going to take all of that together and we're going to distribute it to clear out the parentheses. So all of that times 1 is itself. 2/3 times x plus y to the negative 1/3. Sorry, that's a negative 2/3. I can't read my own handwriting on this thing. Then we're going to add to it. We're going to distribute it to the next term. So that is going to be times 2/3 times x plus y to the negative 2/3 times dy dx. Don't forget there is an equal sign here. So equals dy dx. So then what we're going to do is we are going to move all of the terms that do not have a dy dx onto one side of the equation, and all of the terms that do have a dy dx are going to be moved onto the other side. So I'm going to subtract this dy dx. And while we are at it, I am also going to get rid of this first term that does not have a dy dx in it by subtracting it from both sides. So what that will get us once we do all of that subtracting is we were going to get 2/3 times x plus y to the power of negative 2/3 times dy dx minus dy dx equals negative 2/3 times x plus y to the negative 2/3. Now that both terms on the left have a common factor, we're going to factor out a dy dx out of each term on the left-hand side. So I'm going to factor out the dy dx and write all of the leftovers in parentheses. So what's left over out of that first term is this 2/3 times x plus y to the negative 2/3. Then what's left over out of the next term is minus 1. And don't forget that equals 2/3 times x plus y to the negative 2/3. So then I'm going to finish getting dy dx by itself by dividing both sides by 2/3, by all of this. So we're going to divide both sides by everything that is in this parenthesis. So when you divide both sides, you're going to get dy dx equals negative 2/3 times x plus y to the negative 2/3 all over 2/3 times x plus y to the negative 2/3 minus 1. And for something this complicated, that's fine as long as dy dx is by itself. So for this next one, we're going to go back to the equation of the unit circle, x squared plus y squared equals 1. And we're going to be finding d squared y over dx squared. So if you remember with Leibniz's notation, this is the second derivative. The second derivative is the derivative of the derivative. We already found the first derivative, so we're not going to go through all of that again. The first derivative we found several slides ago was negative x over y. So what we're going to do is we are going to take the derivative again, and remember, we are taking the derivative with respect to x. This variable on the bottom is the variable we're differentiating with respect to. So what I'm going to do is I'm going to go from here, from this form, and I'm going to take the derivative with respect to x of both sides of this equation. So one advantage of getting dy dx by itself is that, when you take its second derivative, derivative of dy over dx is going to be d squared y over dx squared. So at least that is by itself. However, for the other side, we are taking the derivative with respect to x of negative x over y. This is a quotient, and it requires a quotient rule. Negative x is the top function, y is the bottom function. So we're going to start off with the bottom function left alone, times derivative of the top. Derivative of negative x is negative 1. Then we're going to minus the top function left alone, times the derivative of the bottom. Remember, we're differentiating with respect to x. So the derivative of y with respect to x is dy dx. All over the bottom function y squared. And no, don't leave it like this. Even though d squared y over dx squared is by itself, don't leave it like this, because you really just want your second derivative in terms of just x's and y's, and we've got this dy dx in here. We do not want the second derivative being defined in terms of the first derivative. We don't want to leave it like this. So we need to replace dy dx with something. So dy dx equals negative x over y, so I'm going to replace dy dx with negative x over y. And I actually am going to do quite a bit of simplifying here. So that will give us negative y. Negative times negative is a positive. X times negative x over y all over y squared. Now continuing to simplify, I'm going to work on simplifying the numerator. So x times negative x over y is minus x squared all over y. So what I'm actually going to do here, you might recognize this as a complex fraction. Complex fractions can be simplified. The way to simplify complex fractions is to do any addition or subtraction in the numerator first. Then you're going to tackle the division of fractions. So I'm going to take these two terms, I'm going to turn that into a fraction by putting it over 1. And I am going to find common denominators between those two fractions. So the common denominator between 1 and y is y. So I'm going to multiply both the top and the bottom of this first fraction by y to get a common denominator. So that will give us negative y squared all over y minus x squared over y all over y squared. Then once you find that common denominator, you are going to then carry over that common denominator y and just add well, in this case, subtract the numerators. So we'll get negative y squared minus x squared all over y squared. You may also notice that between negative y squared and negative x squared, there is a common factor of negative 1. So I'm going to factor a negative 1 out of these two terms. So I get y squared plus x squared all over y all over y squared. Now, y squared plus x squared. This actually equals something. So just take a look on this page somewhere. There is something somewhere on this page that says that x squared plus y squared equals something. X squared plus y squared is equal to 1. So I can actually replace this y squared plus x squared with 1. So negative 1 times 1 is negative 1 over y, and that's all going to be divided by y squared. So now that we have the top fraction, the numerator expressed as one single fraction, we can think of this as division of fractions. So we're going to keep the top fraction as is. We're going to change the division to multiplication, and we're going to take this bottom fraction and we are going to flip it over to give us 1 over y squared. Simplifies down to negative 1 over y cubed. So your second derivative, d squared y over dx squared, actually simplified down to negative 1 over y cubed. So that was how to take a second derivative using implicit differentiation. You are going to have to substitute that dy dx in for the first derivative. So that is it for implicit differentiation. In the next videos, we're going to be covering more derivative rules because we haven't even touched logarithms and inverse trig functions yet. So we're going to be covering those in the next couple of sections. So thank you all very much for watching, and I will see you guys in the next video. Bye-bye.